All right, thank you very much for the introduction. Thank you all for being here. I'm quite excited to be actually back in this room. I was here more or less exactly 1 year ago, already giving a talk, and I'm really looking forward to talk to you today about anchors, which is a nice explainable AI method that allows you to uncover not so much what a machine learning model is looking at, but what a machine learning model relies on to make its decisions. So in general, just to give you a rough idea, what's the big question? We're quite often faced with a situation that we do have a machine learning model that takes some input, maps it to some output, and then either we as the people creating it or somebody who's trying to audit it or even the users that are interacting with the system, they wonder why this is actually happening. Or they might come to you and they wonder why under these circumstances did your model do something. And that's a very big question, and there are many different ways that you can answer this why, and anchors is just one of many ways in which we can do that. We have a lot on our agenda today. What we're going to do is to first talk about what's an anchor in more general terms, so what's the basic idea. Then we will talk about how we can define these anchors in terms of rule sets. Then we will look at basic strategies for finding them, right? So how do we find out what a model relies on? Then we will take a bit of more of a deep dive into a multi-arm bandit algorithm that allows us to do this efficiently. And finally, we'll be able to assemble a complete anchor algorithm. Now, if you've looked at the extended abstract, you will have seen that it mentions that I would actually be, or we together would actually be coding up such an algorithm today from scratch. Unfortunately, it turns out it's not possible, or at least I couldn't find a way to do this in 20 minutes, while also making sure that we cover all the concepts that are really important to understand. And so I hope you agree with me that it's the right decision to instead focus on these concepts, to really grok them, rather than trying to code up a basic version and then everything flies over your head. But even without coding, there's a lot on the agenda, so let's jump right in. What is an anchor? If you look at this picture and you try to figure out in which country this picture was taken, if you just look at this, most of you will immediately know or guess that this is a picture from Germany. And then if you wonder how do you know that? How did you figure this out? I mean, there are a lot of things you can look at, right? The houses, the cars, maybe the traffic signs. But there's one thing which kind of gives it away, which is this orchid, right? So this yellow sign in the center, that's very typical for Germany. That doesn't exist anywhere else in the world. And so independent of what else is in the picture and what else you've been looking at, this is really where you anchor your decision on that this is probably most likely a picture from Germany. Another example would be this guy. Quite a timeless picture in principle, right? Gray background, wears a suit, wears a white shirt. It's not really possible to really guess where this is and also not when this picture was taken. But I guess most of you will be able to kind of time that picture, put it like on a timeline, put it on the calendar, just because for the sole reason that this guy has an iPhone in his hand. And so we know that this cannot possibly have been taken prior to the existence of iPhones, right? So this is not a picture from the 90s. This is also not the early 2000s, but it has to be post-2007. And so even if you don't know who that is, or where this could have possibly been taken, just the fact that there's an iPhone in that picture kind of dates it. And so this is the general colloquial concept of an anchor. This is something which, as long as that is present, as long as this is in the picture, for example, you will maintain that decision and would be really, really difficult to convince you that, for example, this picture was actually taken in 1985. Anchors can also be interesting, right? For example, if you look at this picture at first glance, you might think that's Paris, right? There's the Eiffel Tower. And you wouldn't necessarily be wrong, right? But this picture has actually been taken in Las Vegas. But if somebody came to you and said, well, I think that's a picture from Paris, you probably wouldn't be so mad at them when they point out, well, there's the Eiffel Tower in the picture, where else could have possibly been taken? And these situations like this are actually the ones where, mostly in data science, these anchor algorithms are really helpful because machine learning models tend to make exactly these kind of mistakes. They look at a certain thing. They have seen a lot of samples from pictures of the Eiffel Tower in Paris, so they locate this picture in Paris. And then actually once you know why was this picture placed in Paris, you can then go and maybe augment your data set. Moving more towards machine learning, we can refine our definition of an anchor. We'll be working through that over the next minutes, and say that we will define an anchor as something that, as long as it is present in the input, the model will maintain its output, right? So as long as there's the Eiffel Tower, our model will constantly tell us that's Paris, that's Paris, that's Paris. And if we want to actually have it recognized that also Eiffel Towers exist elsewhere, we need to add more data. And the example we'll be working with is not going to be an image, but it's going to be a sentence. We will use a kind of a sentiment analysis model, and we'll use a sentence which is Python is the best programming language, to which this model assigns a positive sentiment. And using this example, we will try, or we will start to understand how anchors can be computed for that sentence. So far, anchors are quite a vague term, right? So we haven't really defined an anchor in a way. We've just talked about it. We've pointed at pictures. You maybe have a guess of where the anchor sits in that sentence. But we need to be a bit more specific. And the way that anchor algorithms do this is by creating rules, by defining anchors in terms of rules. And we can do this immediately for our example sentence. By just coming up, so we have 6 words, and so we can come up with 6 rules, 1 rule for each word. So does the sentence contain the word Python? Does the sentence contain the word best? Does the sentence contain the word programming? And so we have 6 rules. And what you will already notice is that these rules cover the entire sentence, right? And we know that probably 1 or 2 or 3 of these rules, so like the presence of certain words, is going to lead to our model, or is going to make our model predict a positive sentiment for that sentence. And so the question is, which of these 6 rules is it? There are different types of rules that you can use. The simple version are binary rules, and that's anything which you can encode as a true or false statement. One example which we've already just seen is the presence of a certain token or the presence of a word. We can also do, when we're working with images, might be the presence of a certain pixel or a certain image segment, right? The Eiffel Tower, the iPhone, the Ortsschild. Or if we're in the tabular numeric data space, it might be that there's a certain feature that surpasses a given threshold. So let's say every time a certain value is above 1,000, we will make a certain prediction. Of course, there are infinitely many possibilities of defining rules. You can also have more complex ones, and I would just define everything that requires more than 1 bit to encode as a complex rule. And typical examples would be if you have a feature, a scalar feature that has a lower and an upper bounds, right? So if you sit in between a range, then this rule would apply, or you maybe have a categorical variable that can take on multiple values, and as long as it has a value out of a subset, then this could also be a rule that is fulfilled or not fulfilled. Yeah. And so we can continue refining the definition of an anchor, which is to say that an anchor is a set of rules. And as long as all these rules are fulfilled for an input, then the model will maintain its output. So it's not going to change from the original. And this definition allows us to come up with our first anchor of the day, which is quite trivial, but also instructive to look at, which is just to say all of the rules that we have should apply. Right? We know that if the sentence contains the words Python is the best programming language, we get a positive sentiment. That fulfills our definition, right? So we have these 6 rules, all of them apply, we get a positive sentiment. But of course, it's not really helpful, right? So it doesn't tell us anything more than what we have already learned. So maybe we need to be a bit more specific of what we want to find. And at least a good start is to look for the smallest set of rules, such that this relationship, that set of rules applies to the input, leads to the model yielding a certain output, that this holds with high probability. And so we're not interested in having many rules, but we want to find the smallest set of rules. And using our example, we already can make an assumption of how many rules we might probably need and what this should look like. So the idea is that we have the sentence, Python is the best programming language, our model predicts a positive sentiment. And intuitively, we already would assume that, for example, if we change the programming language, like Java is the best programming language, then this might not be a true statement, but nevertheless, the model will continue to believe that this is a positive statement. However, if we switch out the word best for the word worst, then we would assume at least that we get a negative sentiment, and so quite likely the anchor in this case would be, does the sentence contain the word best, or does the sentence contain the word, or the words the best, for example. But instead of just looking at sentences, how can we actually teach a computer to find this, also, of course, in more complicated scenarios? And to find an anchor, we use something which is called a local beam search, or at least a local search. And that's a very common algorithm. Some of you might have worked with that during, if you have a computer science degree, you might have learned about this, or if you've done work in general in search or in planning, for example, then search is quite a common structure. And this works by just selecting one random rule, starting with one single random rule in the beginning. For example, does the sentence contain the word programming? And then out of this rule we'll derive the so-called next generation, which we can, for example, generate by just adding an additional random rule to it. So we have three possible children, or three possible new anchors that might be anchors, right? And then we have these three options, and we can go through and figure out which one of these is most likely to give us a positive sentiment. So, right, is it the word programming in is it the word programming in Python, or is it the words programming in best? And then if we do this, and if we try this a lot of times, over time we will find out that actually the bottom one, so if it contains the word programming and it contains the word best, that this is the best option, and then we could either stop or we could continue and add yet another rule and try to see if we can get even better and even closer. Two things to note here. You will see that if we just start with one rule in the beginning, we will never get rid of this word programming, even though it's probably unrelated to what we're trying to figure out. So if you do this as a beam search, what you will do is that even in the first generation, you will start with 2 or 3 or 4 different rules, right? So that you have independent starting points. And the second thing is, how do we actually know which of these we want to keep, right? So each generation, we want to look at a lot of new versions and then just keep a handful of them and then evolve them further. And this is where these multi-armed bandits will come in eventually. But first, let's zoom in and look at how do we actually evaluate such an anchor candidate, right? So how do we know whether this might possibly be an anchor? Again, taking the example of the sentence contains the words programming in best, what we do is that we look through a lot of sample sentences. And these can either come from a big body of text, right? So you might have a big text database or a big text data set, which you can look through, or you can also generate them by modifying the original sentence, just swapping out certain words or just deleting words from the sentence. And we will look through all these sentences that we have, all these samples, until we find a sentence that matches our rules, right? That fulfills the rule that it has to contain the word best and it has to contain the word programming. And once we have found that sentence, we will then go and feed this sentence into our model. And then the model will either say it's a positive sentence or a negative sentence, and this gives us some hint, right? So then we learn a little bit more about this set of rules. It doesn't tell us anything, but at least it's a sign in either direction. And to do this a little bit more efficiently, we can use so-called multi-armed bandit, a multi-armed bandit or multi-armed bandit framework and frame it as such a problem. And the idea of a multi-armed bandit, very roughly speaking, is that we have different arms, which in our case are just the different candidates, different rule combinations, and we have certain beliefs about them, right? So we're trying to understand whether these rules being fulfilled will lead to a positive sentiment. And we can refine our beliefs or update our beliefs by pulling these arms. That just means run the evaluation I just showed you. And then over time, we will be able to update our beliefs and get closer and closer and closer to the true probability. And that's what we use to rank and understand which of these candidates we generated are actually relevant. Yeah, and now let's get to the algorithm, the specific algorithm that is actually used within the anchor explanation approach. This has a very strange name. It's called KILUCB, multi-armed bandit algorithm. The first thing we will do is, or what we'll do in the next couple of minutes, is to really decode what that means and get an understanding. So the first part of the KILUCB the KL stands for Kullback-Leibler divergence bounds. We will not go into too much detail what Kullback-Leibler divergence is, but in very rough terms, it's a measure for checking how far apart two different probability distributions are. So if you have one probability distribution and another one, it's a measure to figure out are they actually the same, how different are they, and can you actually tell them apart when you encounter them in real life. And this is a basic measure that underlies this mechanism in this multi-armed bandit algorithm, and we will use this concept to compute bounds. Because what's happening, what we have been doing so far is that we had an anchor candidate and we checked it n times, right? So we've evaluated n times, and then we will know that the model produced the desired output, so the positive sentiment, in m cases. And so very naively, we will believe that the probability that this is that this will produce a positive sentiment is just m over n, right? So we've seen it m times out of n, so this is our belief. But of course, if you've just done this once or twice, it's very unlikely that we have the true probability, right? So it might be that it just produces a positive sentiment in 5% of the cases where the rules are fulfilled, and we've just gotten unlucky that we've seen a positive sentiment in the first two attempts. And so using these divergence bounds, what we will do is we can calculate a lower and an upper bound on that probability. So we will figure out what's the lowest true probability and the highest true probability that is compatible with the observation that we've had. And roughly speaking, the more times we try, the more it shrinks, right? So if we tried 100 times, then we will be pretty close to the actual true probability. Yeah, so that's the first part. And then the second part is this LUCB. That's the lower and upper confidence bound. Because if you remember, the way that we evaluate all these different anchor candidates is by checking the model. First of all, we need to search through a lot of text. And then once we find text that matches, then we also need to go and evaluate it by actually sending a text to the model and then receiving it. And that's a very expensive operation. If we start with, let's say, 10 different possible candidates in the first generation, and then we generate 3 new ones out of every candidate, then we have 30, and we need to shrink it down to 10 again. This will take us a lot of time and a lot of compute. And so we would like to minimize the number of times we actually need to query our machine learning model. And the way that we can do this in this LUCB setting is to do the following procedure in order to find the best n candidates out of a set of, let's say, 2 times n or 3 times n. The first thing is that we sort the candidates based on our current beliefs, right? So we have a very naive understanding of how these would rank. So some we've never seen positive examples for, some we've only seen positive examples for, and so we will just rank them in order from the best to the worst. And then instead of checking all of them again, we will just look at the nth candidate, so the one we're just about to keep, and the n+1th candidate, so the one which we're just about to drop and not consider further. And we will only refine our beliefs about these 2 candidates. And then what might happen is that they just stay in their place, or they swap positions, or they move somewhere entirely different. And that's fine, but we will just continue doing this over and over and over again. And what will then happen is that we kind of have a leading pack. So the top, let's say we keep 10 candidates. So the top 10 will slowly start to move away from the bottom pack. And we will continue repeating this until the lower bound for the nth candidate, so like the worst case scenario for the one we're just about to keep, and the upper bound of the n+1th candidate, so the best case scenario for the one we're going to throw away, until there will be a gap that's forming. Once this surpasses a given threshold, that's a hyperparameter of the algorithm, we are fairly confident that we've actually figured out which are the best ones to keep, and then we'll use them in the next iteration. And this way we can minimize the number of queries we need to make to our model. Yeah, so then now we do actually have all ingredients, and we can assemble them together to form an anchor algorithm. And the main components of an anchor implementation are, of course, the model. So that's something which we need, obviously, because that's what we want to learn about. And then we have 4 components that we need to create. They might be really simple. They might also be very intricate. And one big problem with anchor algorithms in practice is, or one challenge rather, is that you can tune and tweak all of these independently. And so it can be quite tricky to come up with a good combination of parameters that reliably generates what you're looking for. So the first part is the rule generator, right? So far, in the example that we've talked about today, we've mostly, we've just like looked at single words. We've just looked for the presence of words. For example, we haven't looked at word order. These are all things which we could potentially implement, but we need something which generates these rules for a certain sample. Then we need the search components. The search component, and there I would say it's the setup I showed you is fairly standard. But what I've shown you today is a very simple version of generating this next generation. So we've just been adding rules. We've never deleted rules. Potentially, we could also do this backwards, right? If we just have a really short sentence, we could just start with all the rules in place and then just take random ones out. Lots of different possibilities. You can also go into evolutionary and genetic algorithms. So lots of things to explore there. And then, in order to figure out which of these anchor candidates to keep for the next generation, we used a multi-arm bandit algorithm, usually based on this KILUCB system, which is mostly in place to ensure that we don't need to query our model that often. And in order for these multi-arm bandit component to work, we need a sample generator. So we need either a database or some way of generating these disturbed sentences so that we have something to evaluate against. And with that said, we're pretty much in time and also have a complete anchor algorithm at our hands. And so I would like to thank you for your attention. I'm really looking forward to the discussion we're about to have. And and there's a GitHub repository for this talk, which contains both the slides and also a fairly long list of links for further reading, links to implementation, links to research papers, and more accessible tutorials on this topic. And I'm looking forward to your questions now. Thank you.
Great, thank you, KIlian. We have a couple of questions on the Slido. Keep voting if you want to upvote some questions. First one, would it be possible to use a priori search, like A rules, to find the best candidate rule set instead of the seemingly costly local beam search plus LUCB?
To use what exactly? So I'm not familiar with A rules, with that concept, but in general, yes, you can go in with whatever information you have, and also depending on who you want to show these explanations to or what you suspect that these anchors should look like, you can of course tweak your rules according to that. And the more you can put in as a priori information, the better. But on the other hand, you also have to make sure that you're actually figuring out what the model is doing and that you're not just creating something which you believe that it should be doing.
Thanks. For now, I'm taking the question in order because it's all 0 votes. So please look at the Slido and upvote if you find.
You haven't reviewed them.
Yeah, I reviewed them.
This is why we can't review them.
Oh, no. Because I'm online, I'm reviewing. I approved all the question facts. Okay, so let's go for the next one.
Yeah, sure.
For what kinds of models and data, tabular, images, text, would you most recommend using anchors?
I think actually, so it works for all of them. Where it's quite helpful is for tabular data, but there the rules are a bit more complicated. But there it's really nice because you can also then go and search through your data set and find other real samples that fulfill these conditions. And then this also allows you to compute the coverage, right? So you know how many, do these rules only apply to a very specific subset, or is this actually very general for your entire data set?
Okay, skip this one, is the same. What framework do you recommend for production use?
That's a difficult question. So in my experience, it actually makes, if you really want to use that, it actually makes sense to more or less code this up in the specific way that you need it. So you can use the KLUCB algorithms. That's like a fairly small function. Also, the search is not super difficult to implement. But everything else is really has to be tailored to your use case, right? So like the rule generation, the way that you perform the search and generate the next generation of potential candidates is something where it makes sense if you need this in a performant fashion, to really code this up yourself. And the most mature implementation that I know of is in the Alibi package by Selden, which is also linked in the GitHub repository.
Nice. How do the anchors generalize? How well do they work on unseen data?
On
unseen data.
I would say that depends, right? So if your model is quite consistent in what it's doing, and the examples that you generate these anchors for are also like well within what the model can handle, then they do generalize quite well. Otherwise, you're doing something wrong in generating them. But the idea is to find out, to find the general rules. And of course, that's easier, for example, in tabular data rather than in image data, just because the dimensionality of images is way higher, orders of magnitude higher than, let's say, for a tabular data set.
Nice. Just for the audience, a quick question. Do you still not be able to vote on the Slido? I'm really sorry, because I'm approving everything. And I'm connected to the Wi-Fi. So next one, do you think this fits a classification model with 100+ continuous numerical input features?
That's probably computationally expensive, but there's no reason why this shouldn't work. It will just take a really long time. In general, anchors only work for classification. But if you, for example, have a regression model or something which is quite close to a regression model, there's always a way to turn it into a classification problem by discretizing the output and potentially also by discretizing the input. So if you have continuous scalar inputs, what you usually do is that you divide this up either in 10 segments of the same, or 10 intervals of the same size, or you can base this on some statistical property of your data, but you will not have a rule that has a precise value in the beginning, but you need to chop it up in a way that's suitable to the domain you're working in.
Okay, next one is, can you explain the difference to a principal component analysis?
I can try. So the principal component analysis, that's a tricky question. But I would say that this has more to do with the data, right? Rather than with what a model is doing. So the advantage here, and of course, if you can do a principal component analysis on your data, and then this also has something to do with your, it also affects the prediction, kind of. Then you're more on the modeling side of things. Whereas here we're faced with a model we know nothing about, right? So we just have some black box model which we can do nothing but probe it. So I would say that that's essentially unrelated concepts.
Yeah.
But if anybody knows
different.
more about this or has a different opinion, curious to learn about that.
Okay. Do you have some example of applying anchors to computer vision?
Yeah, so I think in general, so there are some examples even in the original paper of how to do this, and the basic idea is actually quite close to what we've done here, right? So it's about classifying images and figuring out which parts of the image you can black out or replace. And that can be quite instructive. For example, what you can, if you're afraid that, for example, what your classifier is looking at is actually, for example, some text in the image. I think there are some common cases from from medical imaging where they figured out that actually what the machine learning models were looking at were like some information written in text on X-rays rather than structures in the X-rays. And this is something where it might be difficult to see this with feature importance methods, because just like humans, I mean, we also look at essentially the entire image, but then still base our decision on a single fact. And there, for example, anchors are quite nice to figure out these kinds of errors where you actually focused on something, or the entire decision depends on, let's say, the credits in the bottom lower left instead of actual image content.
Okay, so last question for speaking about feature importance. Can we extract feature importance with anchor? Can we quantify the impact weight of every rule?
So in principle, anchors and feature importance are two different ways of explaining models, also because they ask two different questions. Right? Feature importance asks which input features had a positive or negative influence on the specific output, and anchors ask what's kind of the deal breaker, right? So what's the part that, as long as it's there, no matter what else we change, it will lead to the same output. And for example, if we start to remove parts of that image in this hypothetical scenario, then the feature importance measures will change drastically, right? So if you black out half the image, our feature importance distribution, if you do Shep or Lime, might look very, very different from what it would look for this image, but the anchor will stay the same. So it's just two different approaches, two different questions. But of course, you can then look at what's the feature importance within your anchor. There are probably lots of ways to combine the two, but in general, it's two very different approaches suitable for different purposes.
Great, thank you, KIlian. Thank you.